Okay, now, okay, all right. I really want to do something on the Greeks because we always hear about the ancient Greeks and how much influence they have given us the Western Empire, Western civilization, and I want to try to impress upon you today just how amazing and how genius the ancient Greeks were during this time, and they completely transformed the Western society. Once the Western scholars started getting the actual Greek works from the Islamic traders, then it took basically jettisoned the Europeans out of the Dark Ages, and it created the Renaissance. So I hope I can impress upon you just how important the Greek civilization, the ancient Greek civilization, still for the Western civilization. Okay, so that's why I really wanted to talk about it. And I'm going to focus more on the mathematics part of it, but really, mathematics, philosophy, all these things are kind of related. And I'm also going to talk a bit about deductive and inductive logic, reasoning, and how that plays a role in mathematics, and that the Greeks were one of the first to actually discuss what deduction and actually induction was. So I hope I can impress upon you that. Well, I want to say first thing to sort of back up. All societies, all complex societies, okay, in some way have some sort of math and sciences. And you can say it from either the Mayan Empire to Africa, obviously Egypt. Everyone has developed math and science to some degree. And there's actually 4 main areas that will develop math and science. And what's interesting is nowadays, math and science is actually creating our society. Before, society was creating math and science. Now math and science is actually affecting us. Like, for example, computer science is just a good example. But in the ancient times, 4 big things really created what we know, created basically the birth of knowledge. And one thing is religion. It sounds kind of funny, right? There's always this science versus religion kind of idea. But in fact, you're going to see, especially with Pythagoras, that actually religion plays a huge role in the development of mathematics, like with Pythagoreans. Even in Europe, a lot of the mathematicians like Descartes, Leibniz, they were actually Christians. So they thought that, if I can understand the world, I can understand God. So it was like that idea. So religion plays a huge role. And with the Pythagoreans, they were a sect. So their sect actually created amazing mathematics. And we'll talk a bit about that as well. The other thing is practicality. Well, that's pretty obvious, right? When you want something done, you resort to, basically, as you say, the invention is the mother of inventions is basically necessity, right? So for example, the ruler, if you want to measure something, well, how do you measure something? You do slots, measuration. Okay, how many slots do you have? Well, then you have numbers. You go from counting like 1, 2, 3 to abstract. Now you start using your fingers, and then it turned into numbers. So basically, we went from the specific cases to abstract cases. And this is where practicality starts to take form. So when we have, like, for example, carpentry, you're going to use, right, actual numbers and design for that. So engineering is a great example of practicality helping our society. So bureaucracy is another one. Interestingly, taxes. I always tell the students about taxes, and why do we need taxes? Well, if you back up and you think, well, when you had this complex society getting more and more complex, and you had, like, for example, you had agriculture, and then you have more and more land, and then the next door neighbors say, you got all this land, I want your food, right? And so what they do is they're going to invade you. So how do you stop invaders? Well, you have to create armies. Well, how do you create armies? Well, you got to raise taxes. Well, how do you raise taxes? You're going to charge everyone the same rate of taxes? No, right? So what they did is they say, well, why don't we take your land and measure the volume or the area of your land? Well, how do you measure area of your land? Do you see what I mean? And you get taxes, you get accounting. So that also really has developed math and science. And the last thing is closely related, but more for today: royal patronage and grants. So a lot of you guys, who have PhDs, you had to get money from, grant money, and that's how you got it. And this royal patronage was really how Descartes, Leibniz, and all these folks were able to survive. Bach, even as a musician, all these guys, all these people from the 17th, 18th century, they had royal patronage. That's how they were able to survive. And so with kings and emperors, by supporting these people, they actually, in turn, developed the math and science. So you see these big four keys, and Greece is no different. Okay? So in Greek, in the Greek times, the early times, we had the Pythagorean theorem. And Pythagoreans, I'll show you later, were actually a religious sect. Okay, so very interesting. But they developed, everyone here knows the Pythagorean theorem, but they developed more than just that. Hellenic period. Then you had the Golden Age. And then finally the Hellenic period. This is really one of the best parts of Greece history, in my opinion. Euclid's elements. I'll talk about elements later. And conic sections. That sounds kind of strange. You guys know cones? Okay? Everyone here talk about parabolas and lines. I mean, those are things we use in engineering all the time. These circles and things. So, a lot of the things that we take for granted today were developed by the Greeks. Okay? So, math-wise. So, some important mathematical contributions. Just some basic things. Then I'm going to get into some people and then some other things. So, the Greeks believed that through inquiry and logic, they could find their place in the universe. That's new to a lot of folks. A lot of people just relied on religion or religious ideas. They actually believe that if we can determine our place in the universe if we use certain methods. Can we get rid of bias? And that's where logic and reasoning come in. Believed in the power of proof. Okay? So, they believe valid reasoning, true premises, equals sound argument. We still believe that today, right? Comes from, that's when they believed. This was new. Mathematical truths must be proven. So in other words, you just don't guess. People say, well, it looks like something's going to happen, but what does that actually prove? Can you actually prove that it's true for all cases? We take a lot of these things for granted, but it started with the Greeks. And one thing about maths, it builds upon itself. So once you have your basic premises, you can use logic to build on those premises to create theorems. And then you can take those theorems and build more. So it just kind of grows. And the last thing is, this is the legacy, it's still around today, is they believe that everything in the universe can be mathematized. I mean, it's still around. I mean, if you talk to scientists, they think that, if we can find the model of the universe, some sort of model, we should be able to mathematize everything. We should be able to predict what's going to happen. Of course, through chaos theory, though that's kind of being knocked down, but that mathematization of everything is started with Aristotle. But it's still around today, that mentality. Okay? So, let me just go through a few folks. And so, Thales of Miletus, this is, again, you can see, look how long ago it was. BCE. Okay? And he was a person that was a statesman, he was a scientist, and a mathematician. Really, math and what do I say math and science is? Because math and sciences really were kind of one at the time. Okay, if you studied math, you were an astronomer, you studied, everything about the universe, okay, as much as you could. This guy here, he thought that proof could be based on deductive reasoning rather than just experiment or intuition alone. So the problem with intuition, what happens is bias gets into it, right? Everyone knows that. Your bias can be in an argument. So instead of doing that, can we get rid of bias? That's the idea of deductive reasoning. Can you get rid of what you think or you feel is correct? Okay? Socrates, I'm not going to go through all these guys. He just had a few things here, but one of the things about Socrates is the Socratic method. Most of you guys are familiar with that, okay? this really can hone a student's critical thinking skills by asking them, getting the teacher or the guide really to ask the right questions. And the one thing about this is that the teacher does not act as sort of the sage on the stage, as I say. He's he'll be just a guide. He may not even know much about the subject, but he works with you to ask you pertinent questions, to make you question your biases, to question why you say what you say. And, you know, Bertrand Russell said, okay, that it's not the problem. You've got to understand the problem. The difficulty is the problem. It's not what it is. Okay, it's the problem, it's difficult. And by doing that, it forces people to ask, why is this the case? Why is that? So this has really transformed Western ideas when it came into being, when the European scholars got hold of the works around the Renaissance time. Okay? Aristotle, so he's the one that said everything he thought it could be mathematized, provided the third step to the scientific method, testing the hypothesis, and he developed a syllogism. I'm going to go through a little bit of logic, I'm not going to talk much about it, but I'm going to talk about what it is so you understand what a deductive argument is, what an inductive argument is. But he's the one that developed a syllogism, or in mathematics we call it the transitive property. Okay? And the scientific method, if you're not too familiar with it, the scientific method just talks about, it's an epistemological system for deriving and developing knowledge. And it allows people to, create an observation, a question, a possible hypothesis, do a prediction, test it. If that doesn't work, go back to the hypothesis. And then hopefully, if you go around here a few times, can you get a conclusion? Okay, that's the scientific method. And this, a lot of these things were developed, the parts of it were developed during the Greek times. Because again, the goal was, can we get rid of bias? When an argument happens, can I always be correct? That's what it was. They wanted to be correct. Can I, if I think that, the earth is flat, and you think the earth is round, I believe it's flat, but you believe it's round, there's an argument. But if there's a sort of a conflict. But if you can use logical deductions with right premises, they thought that, no, we can prove one answer. No, that the earth is round, I suppose. Okay? So, basic problem solving, I won't go too much in here, so I promise it won't be too heavy. But logic really is a science of correct reasoning, and reasoning is drawing of inferences or conclusions from assumed facts. So again, the key is assumed facts. Okay? And mathematics is built on these things. Mathematics is a deductive system. Okay, not a cumulative system, a deductive system. So I always kid my students, said, would you like me to grade your tests deductively? And students were like, yeah, you must be correct. Yeah, yes, we want deductively. I said, okay, no problem. When you get one wrong, you get 0. Okay? No, we don't want that, right? Okay? The whole point of deduction is if you can find one, it's really induction, but I mean, honestly, if math is built on, if you can find a counterexample, then your theory is thrown out. That's how math is built on. Okay? So 2 general methods, deductive, and the easiest way to think about this is it really goes from the general to the specific. That's the easiest way to think about it. Inductive, if you really want to think about it, goes from really the specific to the general. And the key is the conclusion is never guaranteed. But however, it's an extremely powerful way of reasoning. But once you make a conclusion, quote unquote, or a theory, you need to go back using the scientific method to see if it's correct or not. And you may never know. But these are 2 general, very powerful methods. And obviously, most of us are familiar with deductive. So, quick deductive. This is a nice little graph here. You can see deductive goes from theory, hypothesis, observation, confirmation. Can you confirm it? And then inductive, you start with an observation. Can you make look for patterns? I'll show you some of these where you can see if you can find out a pattern. And then hypothesis, or a possible hypothesis, really. And then can you come up with a theory? And you kind of want to, kind of circle around, right? So this is sort of how it works. This is sort of the, again, general to specific and specific to the general. Can you go back? in my opinion, this is what really makes us human. I mean, you can take something and using, patterns and common knowledge, can you join them together to create a possible theory? I don't know of any other creature, animal that can do that. I mean, it's a really an amazing feat that we can do. But it can also get us into trouble. You'll see. So deductive, I won't spend too much time here. This is the most technical it'll get. Basically, if this means if P then Q, so P implies Q, and it's called modus ponens, and there's also modus tollens, and this is called what we call in mathematics the contrapositive. So again, the Greeks developed a lot of this. These are what we call Euler circles, so obviously they didn't have them at that time, but the whole idea was, hey, if P implies Q and P is true, then therefore Q is true. Okay? And this is very powerful. If not Q, therefore not P. A lot of a fallacy, people say, well, hey, if it's not P, then it's not Q. Well, that's not true. Okay? So, for example, you can say, if it's rainy, then it's cloudy. Well, most of the time it's true, if you make that statement, right? But if you say, if it's not raining, if it's not cloudy, it's not raining. But if you said, if it's not raining, it's not cloudy. That's not true, right? So if you say, if it's rainy, then it's cloudy. But if you did a fallacy and said, if it's not rainy, then it's not cloudy. Don't know, right? But if you say, if it's not cloudy, then it's not rainy, it's okay. Okay? Because if it's not Q, therefore not P. And this is what we use in mathematics as a contrapositive. Okay? Syllogism is the most common people understand. If A implies B and B implies C are true, then A implies C. And this is, again, a transitive property in mathematics. And what's interesting is a valid argument does not imply it being true. Okay? You can make a lot of valid arguments, okay, but it doesn't necessarily mean it's true. Like, in other words, the logic process is correct, yet the statement is not true. That's a good one. Every rocket scientist is an idiot. You see. I don't know. Who can I think of? Einstein is not a rocket scientist, therefore Einstein is an idiot. It's correct, but it's not true. Okay? There's an example. Okay? Here's a classic one. I think most of you guys, if you studied any kind of philosophy or even mathematics, you would have seen this one. This is a classic syllogism. All men are mortal. Major premise. Socrates is a man. Therefore, Socrates is mortal. And you can see, because this is easy to visualize with Euler circles. Sometimes they're called Venn diagrams, but Venn diagrams are very specialized the way they look. But the Euler circles are easier to see. And you can see, like, everything mortal, all men, right, are inside the mortal circle, right? And then therefore Socrates is inside the men circle. Well, then, of course, by nature, Socrates must be inside the everything mortal. And this is the start of set theory. So I don't know how many are familiar with mathematics, but mathematics is built around sets. It hasn't been people think math is about numbers. Sorry, for the last 150 years or so, math has not been about numbers. It's been about sets. We talk about sets. Even if I say the set of all integer numbers, okay, I say the set of, or the set of all real numbers. Mathematics is about sets. Okay? And here's the one that's invalid. All people are mortal. Some mortals are students. Therefore, some people are students. The problem is some, right? When you have a sum, it could be out here. But it doesn't say, it doesn't show at all that students could be people. But we know it's not true. But just by the Euler circles, it doesn't work. Okay? And you can make something up completely ridiculous. All quats are quams, all quats are quims, therefore, some quams are quims. It works. It doesn't matter, right? Because the whole point is to show a process. A process. Oh, it's kind of cool. I like it. Quats and I mean some new words, like quats and quams, quats and quims. There's a good tongue twister. But it doesn't matter. The thing is, the whole point is, it's not the... You don't worry about these guys, what a quat and a quam. That's not the point. The point is, what's the process? The process of argument. Enthymemes, there's people who have heard of these. Incomplete arguments that exclude a premise because it's considered obvious. A good one I have here is, John goes to Harvard University, so he must be very intelligent. What's it implying? Everyone goes to Harvard, must be smart, right? We don't know. Maybe. We don't know. We do this all the time. So the whole point is, we want to get rid of bias. That's what the Greeks did. We always are trying to get rid of bias. You can never get rid of all bias, but you try the best, and that's what the Greeks want. They want to say, hey, if we're going to build a system, if we're going to tell what kind of universe we live in, we've got to get rid of bias. Superstition. That's what they thought. Okay, quickly, and then I'll move on to the rest of the Greek parts, but I find this interesting. Inductive reasoning, very powerful, but can get us into trouble. Here's a good one. The doors to the kitchen, living room, and bathroom are all green. Someone can say, well, therefore, all doors in the house are green. Doesn't prove it, right? Because if you find, all it takes is if you just go to one room and you find that the door is not green. It's done, right? It's done. It's called a counterexample. So that's how math works. Once you find a counterexample to your theory, the theory is dead. But it's a powerful way. We can say, we can possibly make a theory that, hey, maybe all the doors are green. Maybe you're correct, maybe you're not. We don't know. Okay, but at least gives you an indication of where to go with your theory. Another one. Every time I drink milk, my stomach aches, hence I'm allergic to milk. People do this with health all the time. Right? It helps us. It could be correct. It may very well be correct. But maybe not. Maybe you had a bad glass or something inside the glass, or maybe the milk that you're drinking out of has something wrong with it. And if you drink some more milk, you'd be okay. You don't really know, right? But this gives you an idea of a theory you can play with, and you can go back and test it. That's the point. Okay? Really powerful. Another one, all mammals observed breathe. All mammals must breathe. Observed, right? Now, I'm pretty sure that the definition of a mammal is something like a creature that breathes, right? But I mean, you've only observed, it's what you observe, right? Okay, it's possible, it's true. But anyway, it gives you an indication of, it allows us to try to make sense of the world around us. Okay, here's one. Given the following number sequence, can you use inductive reasoning to guess what the next one should be? This is a classic example in mathematics. 2, 8, 18, 32, 50. Anyone know? Can you make a guess? And you can play with it, right? You don't really. I don't really know. So in math, you can say, well, they're all even. So can I divide out of 2, right? So I get 2 times 1, 2 times 4, 2 times 9, blah blah blah. Well, now I'm getting something. Yeah, it looks pretty good, right? It's looking better, and I realize these are squares. So I say 2 times 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. What do you think the next one should be? Yeah. Are you sure? Are you 100% sure? In mathematics, you're not. Until you do something called mathematical induction. Once you do mathematical induction, then you can show it's correct. But you make an inference, right? You say, yeah, following the pattern, it must be 2 times 6 squared. But you don't know. You see, sure, it looks obvious. But the whole exercise is it's not true until you go back and prove it. And with mathematics, we call it mathematical induction. Okay? So, yes, we do this all the time. When you do proofs in mathematics, you want to, sort of do some lateral thinking to look at other ideas. Can you bring it together? Can we look at the problem from this perspective, that perspective? Try to make some theories, right? Possible hypotheses, then create a theory, and then will it work? Can we use the principles of mathematics to prove what I hypothesize? So, what about this one? Ooh, this one's a little more tricky. And you might not be able to see it back there, right? I mean, this is both. You got to use both logics here. So I'll give you a little bit of a shortcut, if you want, unless you want to try. You guys want to try? there's a lot of things going on here, right? You got to choose one of these guys that would fit this pattern. And so if you sit there and play with it for a while, what you'll realize is, and I'll just sort of jump to it so we can move on here, but here you notice, if you work this way, you notice there's 1, 2, 3 white dots, right? And then notice that, yeah, there's a black dot here, but maybe that could be there. There's a black dot here, maybe the black dot here, maybe there's another one here, I don't know. But if I look at the white ones, I can see, wow, I've got a white one here, and then now a white one's here. So it looks like it's being, one's coming here, one's coming there. And then over here, you can see, well, this one's missing. It's going here. Which one could it be? Could it be down here or up here? Which one do you think it should be? I heard, someone saw. Someone told me. I mean, you have to, this is the whole idea, right? You got to play with these things. Come up with theories. Can you prove it? So that was my theory, and I turned out to be correct. It's got to be this one. And if you notice, right, because the way the white dots go, here, and then here, but we don't know what's here, but if it was here, then now this is disappearing, and now that's disappearing. Right? And then that was disappearing. So I can say, comes to that one. Okay? I mean, have you guys seen these? You've seen things like this, right? But how do you work to figure them out? You figure them out by looking at patterns, trying to come up with what could be the next one. And the black dots seem to work out too, because they got 1, 2, 3, and then 4. And this one disappears, and that one disappears. So you could go with the black dots as well. Seems like that would work. Anyway, it's just an exercise, amusement, really. But when you think about these things, that's what we're doing. We're using our human qualities of trying to look for patterns, and then trying to come up with does that pattern work? Okay. I mean, the basics of math is space and quantity. But it was a man, I say man in general, who took those things and using logical deductions, built upon those things, those foundations, and just expanded the subject, the complicated subject we know today. Okay? All right. So I'm done with that. Okay? Maybe a little bit too much, but you can understand this is a legacy. This comes down even to today. Pythagoras of Samos. I had to look at a map to find out where Samos is. It's very close to Turkey. I was surprised. Yeah. So remember at the beginning, I talked about religion being a major driver, at least originally, of math. Well, Pythagoreans were actually a religious sect. And what's great about them is they included women as well. And most everyone knows Pythagoras' theorem, okay? But he also talked about harmonic series. The thirds and the fifths and so on and so forth. But this group, I mean, if you read about them, it's really interesting. They couldn't eat meat. They couldn't touch a white chicken. I mean, it sounds stupid, but that's what it was. They couldn't do these weird rules, right? But they were a religious sect, and they were sworn to secrecy. There was a story about one of his followers found that when he did the Pythagorean theorem of 1, 1, and that length of this side is square root of 2, well, the problem is he found that square root of 2 is an irrational number. Okay, so an irrational number is a number that when you work it out, it doesn't repeat the decimals, and it keeps on going. But in the Pythagorean sect, that was heresy. And so basically Pythagoras or one of his followers told the guy, keep quiet about it. Don't let this out. It sounds strange, but that's what's true. Well, the guy couldn't help it. He let it out. And they promptly drowned him. But I mean, square root of 2, irrational numbers, obviously, it's a very important part of mathematics. So, Pythagorean theorems, for you guys, if you don't remember your theorems or forget, essentially it's where the C, the hypotenuse, is the square of the hypotenuse is the sum of the squares of the two sides. And it's called a right angle triangle. And people look at this theorem as being very basic, very simple, But you have to remember, what did I say before? The power of proof. The Babylonians certainly knew pretty much that this side plus this side equals the length of the longer side, or the hypotenuse squared, right? But it was the Greeks that we know who first gave a proof of the Pythagorean theorem. And now it was about 319 proofs or something. It's tremendous. So the Chinese had a diagrammatic proof around 600 BC. That was really interesting. Go-Gu theorem, right? Yeah. So it's been known. Now, why is this incredibly important? Because it takes area, okay, and transforms it to length. So there's a relationship between length and area. So it transforms engineering. Can you imagine doing engineering without angles? Sine and cos, you guys remember that from trigonometry from when you were little kids? Sine, cos, tan, all these things come from right angle triangles. And it's based upon the Pythagorean theorem. Can you imagine a world without angles? Not angels, angles, right? I always tell my students they spell angles with angels, okay? You couldn't. I mean, especially engineering-wise, you could not, right? I mean, it's a simple theorem, but devastating in its implications. I mean, really. Here's one by U.S. President Garfield. Yeah, the guy was actually come up with his own proof. Kind of cool. Used an area of a trapezoid, and he realized that he said the sum of the bases over 2 and the height. Give this little formula, and you can also compute the whole area of the triangles. And he realized when he did it, he got a squared plus b squared is equal to c squared. Again, the right angle triangle. A squared plus b squared equals c squared. And again, a right angle triangle for you guys, that's where the angle is 90 degrees, or pi over 2 for your more mathematically in tune folks. Okay? But again, this still relates area to length, or length to area. So, very interesting. When I found that out, I was like pretty impressed. I wonder if Obama could do a proof of that. Oh. Okay. Yeah, Trump. Yeah, I don't know. Yeah, maybe Trump could. I don't know. I'm just joking. I don't know. Zeno. Now, I'm moving around in dates here. But again, how did Zeno come to be important? Well, Zeno was one of the first great doubters of mathematics. Again, the idea was, can we take simple axioms, use logical deduction, to join them together to create theorems and to create a bigger system. So can we keep doing that? In other words, if we can get some axioms, some basic axioms, like for example in math, 1 is a number, is an axiom. I mean, that's what it is. 1 is a number, is an axiom. Okay, axiom is something that you assume to be true. Okay, if you have those axioms, you build on other things, and you get more and more complex systems. So what the Greeks did, they did geometry. I'm not going to show any geometry here, but they used a compass, okay, which is, where you can draw circles, okay, and a straight edge. Not a ruler, a straight edge, okay. And through a compass and a straight edge, they thought if you just had a compass and a straight edge, you can't, in other words, you can't put bias into the argument, you know what I mean? You can't just say, well, it's a right angle triangle because it looks like a right angle triangle. I can prove it's a right angle triangle, understand? So the Greeks used those kind of, like for example, the compass and the straight edge to build axioms of geometry. But Zeno said, well, there's some problems, okay? Because he thinks, so he came up with 40 paradox, but he thought that, since senses are illusory, especially illusory of motion, there are some problems in mathematics. But in fact, his paradoxes really improved mathematics. Like for example, the tortoise, Achilles and the tortoise, you guys remember that one? This really improved mathematics. Because, why? Well, if you guys don't know, let me just explain it to you. Here you got Achilles and you got the turtle, okay? And the turtle starts halfway on the line. And Achilles says, oh, you're slow, so you can go halfway, I'll give you that, the head start, right? So the paradox says, well, can Achilles ever beat the turtle? So what happens is, the paradox says, well, Achilles will start running. By the time he gets to the turtle position, the original position of the turtle, what's happened? The turtle's already moved ahead. Right? I mean, if you start the race at the same time, by the time Achilles gets to where the turtle started, the turtle has already moved ahead, right? And then again, right? So from that position, when Achilles starts to go, runs again, when he gets to the turtle's second position, well, the turtle's moved ahead again. And when he does it again, the turtle's moved ahead again, a little bit. So what the argument was from Zeno, well, if illusion is, motion is illusory, Achilles would never actually catch the turtle. Now, practically speaking, it will. Obviously, because it's like it's a velocity time curve, right? Achilles would definitely take over the turtle. But the argument, it's not the practicality of it, it's the argument. People have tried to refute the argument. But there's a lot of actually very interesting arguments against Zeno, but it stood for a lot of things. Now, why is it important in math? Because if you look at this thing, what's happening? Achilles and the turtle are getting closer and closer and closer together, right? And in mathematics, we call these asymptotes. Very interesting. And this leads to something else called limits. Okay? I don't want to get too technical on you guys. Okay? But calculus, for you Chinese, Wei Ji Fen, right? Limits are fundamental to calculus. In fact, in my opinion, I mean, without the idea of a limit, you wouldn't have derivatives. And certainly not integration as we know it today. So what's a limit? The limit just says what happens, for example, as x approaches a number. Approaches a number. Not at the number, but approaches. That's what he's doing. See, Achilles never gets to the turtle. The whole idea is he's going to get very close to the turtle, but not at the turtle. You can do this forever. He'll never actually reach the turtle using this kind of, argument. And we do this in today. Like I say, with calculus, limits. We say limit of x approaches 2, whatever. It's close to 2. Then we look at it from the right and from the left, okay? So we don't actually evaluate at that number. And by doing that, we created something called the derivative, and calculus is probably one of the most useful mathematics we have out now. So anyway, it's just, Zeno has many paradoxes. I believe he was the one that said, if a tree falls in the forest, does it make a sound? I think he was the one that said that as well. I may be incorrect. Something like that. I could be wrong. But anyway, okay, Euclid. The elements. Why has this, which is amazing? Because geometry, as I already mentioned, was something based on, as much as possible, on pure deduction. In fact, if you take geometry in school, you probably had to do a lot of proofs, okay? That the whole idea was, if you make a statement, can you back it up using some suppositions? And what he said was the elements, he created this textbook. And interestingly, all the theorems in that textbook from 2,000 years ago, we still teach today. So that's the key. Math is really kind of immortal. I mean, scientific theories get knocked down from one generation to the next. But mathematical theories are true today as they were 2,000 years ago. So it's very interesting. And at the end of his book, he gives a proof. I'll come back here. 5 Platonic solids that there could not be a 6th. So it's one thing to take Platonic solids, and Platonic solid, by the way, is a shape that has a regular, the same shape on each side, but each shape is regular. The length is the same as the width. So each side is the same length. Okay? And that if you put them into 3 dimensions, there's only 5. Yet through the power of proof, he was able to show you could not have a 6th. It's one thing to show you can make them and build them together, right? Like, see if you can try to build it. But you're never going to know, right? You're never going to know if there could not be a 6th out there. But he showed conclusively that no, there are only 5 Platonic solids. And we use these today. The cube is the most well-known one. Socrates thought that the whole world, universe, could be summed up sort of using these Platonic solids. He thought he thought they were perfect in their form, and that For example, the dodecahedron represented the universe. The cube, I believe, represented the Earth. Octahedron, water, and so on and so forth. He thought he could sum up the universe like that because they're so perfect, as they thought. So Euclid's elements, you can see, and this is again 2,000 years old. Plane geometry, that's the geometry that we know of today when you're in the school, okay? We still use. Number theory, theory of irrational numbers, well, that's after Pythagoras, right? Pythagoras didn't like irrational numbers, but too bad, right? And then the last part, three-dimensional geometry, which included the proof that there's only 5 atomic solids. This is actually a small piece of it. It's kind of interesting. Okay, yeah. Well, I don't want to spend too much time with this one, but this is just an example of the power of proof. So everyone know what a prime number is? Okay, it's a number that can only be divided evenly with its 1 and itself. So for example, 7. 1 and 7 divided into 7. But 2 and 3, 4, 5, and 6 do not. So a prime number only has 2 divisors, 1 and itself. And what Euclid says is, hey, why don't you multiply all these numbers together and then add 1 at it? Because it's based on the proof that all numbers can be written in terms of as product of prime numbers. And that's a proof that he already built it on. So this is based on that every number can be written as a product of prime numbers. So for example, 12. 2 times 2, 2 squared, times 3. Okay, so it's built on prime numbers 2 and 3. So here, he said, if you know that, you put all the primes together, you add 1, okay, and you get this number, n. So there's 2 possibilities only. One is, since n is clearly greater than p, n could be a prime. Could be. Like if I said, what's 2 times 3 times 5? It's 30. 31. 31's a prime. Okay? Or, because it's a new number, but the fact that all numbers are products of primes, there must be some prime not in n. Or in p, pardon me, the set. Therefore, showing that there are infinitely number of prime numbers. See, it's solid. It's done. You don't sit there and count. See, intuition may say, yeah, there's probably enough prime. There's probably infinite prime numbers. I'm not sure. But here it's conclusive. It's done. That there are infinite number of prime numbers. So it's just an example of power of proof. QED, by the way, means quod erat demonstratum. It's Latin for it's demonstrated. Done. Or it's shown. Okay, Archimedes. I'm getting done here. Okay, Archimedes. I think most of you here have heard of Archimedes, one of the greatest scientists and mathematicians of all time. Discovered law of buoyancy. The lever means physics, science, right? You guys have heard of the lever, right? Center of mass, equilibrium, hydrostatic pressure. I mean, this guy was, really beyond his time. He was like Leonardo da Vinci. And one of the things he talks about, which is really funny, is that it was rumored that he was told by a king who was given a crown from a goldsmith, can you tell me, or could you help me determine if this crown is pure gold or not? And at the time, there's no way to tell. Like, you put a bit of silver in the gold, it's probably not enough to make the gold a different color. There's no way to, you just cannot tell. Maybe now, sure, nowadays you can with equipment. But at the time, there's no way to tell if a crown or anything was alloyed with something else. So, it's rumored, or at least the story is, the legend was he had his bath, right? And when he sat in the bath, what happens? When you sit down, the water level goes up, right? When you get up, the water level goes down. What's happening? His weight, his volume is displaced in the water. Okay? That water being displaced is the weight of that water. Weight of your displacement is the weight of the water going up, right? Law of buoyancy. That's why boats can float. Why does a boat float? Because what it displaces, the water it displaces is the weight of the boat. That's why the boat floats. Okay? Equal pressure. Okay? So what he did, if you look here, Okay? He realized when he got out of the bath that, actually, gold and silver are different weights. So one will displace more water than the other if it's the same weight. So the crown, he took an equal amount of gold, pure gold, the same weight as the crown. Okay? And he compared the volume. How did he compare the volume? He stuck it in the water, because if the crown with the silver is going to have more volume per weight, right? So it's going to try to displace more water. Therefore, the gold will sink further than the crown. So therefore, he proved that, yes, the crown did have silver in it. Or something else. I mean, it may not have been silver, it could be anything else. But it wasn't not pure gold. Interesting. Yeah, cool. And yeah, eureka means, I believe it. I found it. I discovered it. Okay. I know it. You've heard of eureka, right? Isn't it like a eureka city somewhere? Okay. Archimedes' law of the lever. This is a famous thing. He said, give me a place to stand, I will move the earth. That's just one of his famous sayings, right? That he was so impressed with the idea of a lever that, you can move, a man could move a heavier object than you could lift normally by using a lever. And you try to figure out why is that the case. So again, this is inquiry and logic, right? They're asking why. It's a key question. Why did something happen? And he came up with we use this today in physics. It's a pretty simple equation, actually. Archimedes and pi, and what he did, why do I bring this up? Because it's like calculus, the idea of getting smaller and smaller areas. He took the polygons, and he noticed that the circle, if you guys remember the area or the circumference of a circle, is 2 pi r. In other words, circumference, it's 2 pi r. So that means it's the radius times 2 pi gives you the circumference of a circle. And he was able to sort of circumscribe the polygons on the outside and then the inside, and he was able to get it smaller and smaller and smaller. So what is that good in mathematics? It's limits. Again, the idea of limits, calculus, and by using approximations, he was able to get very, very close to about 3.1419. That's pretty amazing. It doesn't sound very good, but you have to remember the Greeks did not have a good number system. The Chinese, there was a guy in Chinese that came up with 3.1415. Even more accurate. Liu Hui, I believe, if I remember right. Yeah, or one of those guys. Okay, so another thing they were able to do, Eratosthenes measured the circumference of the Earth within 2% of its true value. I mean, amazing. And what's this? Geometry. So again, basic geometry, and by building on those aspects, building on those facts they found, he was able to calculate the circumference of the Earth within 2% of its true value. And the Earth is not a true sphere. It's actually elliptoid, right? Around the equator, it's a little bit, the Earth is kind of flattened a little bit, right? Stadia is about, I forget the exact stadia, but it's about 36,000 something kilometers, whatever it was, or 39, I forget now exactly the distance, the circumference of the Earth in kilometers. I know in miles, but not kilometers. And what he was able to do is he knew, and this again is astronomy, that at Serene, which is on the tropic of Cancer, so in other words, at June 21st, the sun was overhead directly at noon. And at the same time, somebody in Alexandria, pretty much directly north, also measured the angle of the sun, and it had a slight change in angle. And by figuring out the angles of the circle and the distance between here and there, he was able to work out the circumference of the Earth. Pretty simple, but it works. Cool. All right. I'll skip this one here. I want to get to this one here. This is important. Apollonius, and we're almost done here, but we're getting to the point now, this is moving on in Greek time, getting close to the Roman times, but the Apollonius on conics had tremendous effect on Johannes Kepler, and then therefore Newton, our idea of planetary motion. We would not have figured out that planets move in elliptical orbits without Apollonius' work on conic sections. These are all the math that you guys do in middle school that you hate, okay? Parabolas, lines, ellipses, circles, and without that knowledge, we would almost positive that Kepler would not have come up with his 3 laws of planetary motion, and Newton probably would not have come up with his universal gravitation. I mean, you understand, like, the works, the Greek influence is tremendous. And this, again, once the Europeans got out of the, we're in the Dark Ages, once they got a hold of these documents and started to be able to translate them into Latin and English and so on and so forth, it just transformed people's lives, literally, like within a very short time. Ptolemy, now we're just AD now. The Almagest, before Europeans had the compass, it was hard to navigate. So how they navigate? They had this amazing document by Ptolemy called the Almagest. However, you notice that, what do you notice here? Okay, there is the sun right there, there's the earth, right? Everything's revolving around the earth. But the information in the Almagest allowed people to navigate. So people who had that document could navigate. I don't know if you guys really think about it, but navigation is difficult. It's difficult. It's not easy. You can go by the stars and so on and so forth, but what he did, because this document had the stars and the location of the stars and the moon and so on and forth at certain dates, it was so accurate that people, knowing the date, could look up at the night sky, navigate, okay, this star is here, that star is here, we must be here. So it's kind of it's hard to tell, what's the word I'm looking for? It's hard to impress upon you how important the Almagest was to medieval times, medieval Europe especially. It completely transformed navigation. People were able to navigate. Amazing. And the other effect was, yes, Earth is the center of the universe, and the church took this up, and that became dogma until Copernicus, basically. Ptolemy's map of the world, a bit crazy, right? And the last person I want to talk about is Hypatia of Alexandria. First woman that they know of to make substantial contributions to mathematics. And again, it's 370 to 415 AD. This is a really bad time to be around. Greece was okay, but, well, you know, right? Rome got sacked 408 to 410 by Alec, if I remember the guy's name, Alec something, whatever. He was a barbarian. I mean, they basically sieged Rome for 2 years. People were starting to eat each other and everything else. It was a very bad time to be alive, okay, at that time in Rome. But Alexandria, of course, is in Egypt. But she was not just a mathematician, but she was also a politician, okay, and a pagan in a Christian, now a Christian empire. But she made substantial contributions. She talked about Apollonius' conics and other things. Just to really, and she apparently was an amazing teacher. People loved her. But unfortunately, she was murdered by a Christian mob on Lent. Terribly. She was dragged into a church and forced to convert, because she was a pagan, right? So she was forced to convert, and they murdered her. So, unfortunately, that murder, the way she died, sort of eclipses her actual mathematics, what she came up with. But that's just how history works sometimes. So, I always get my students to make sure they know Hypatia. But there's probably others as well, other women, but we don't know about them. Because remember, the Pythagoreans allowed women into their group. Men and women both did math as a kind of religious sect. That's what it was. Okay, so this really kind of ends the period. She was the last person that we know of to really, from the Greeks, to do anything more with mathematics. You know, the Roman Empire was already starting to go as well. I mean, that whole area, and then of course, I guess the Roman Empire went to the east, right? Went to Constantinople at the time. But things are really falling apart. So this was really the last that we know of anything contributed by the Greeks. But just a couple more. You can see as the centuries moved ahead, many people took the works. Remember I said it was translated, and again, Greek in 800 AD, Arabic, Latin, French, English, Chinese even. Okay, Euclid's Elements was translated over and over again. And that's the thing to realize, that we have the works. There was no photocopiers, right? We have the works because they translated them. Monks often translated them. If it weren't for the Islamic traders, we probably would have known very little about the Greeks. They saved a lot of the Greek works. And then, you know, the church, you know, the monks and so on and so forth, they got hold of these documents and then translated them into English or Latin. And then a lot of the monks, like for example, Mersenne was a monk. A lot of the monks were closet mathematicians. Okay? They saved a lot of these works. So it's really important to understand that it's a copy of a copy of a copy. You know what happens when people keep copying, right? Things change. Every time you make a copy, it changes. So we don't know 100%. You know, we say this is from Plato or whatever, but was everything copied? Was there something missing? Okay, we don't know. But anyway, at least these people, you can see that there's many translations, and these people actually saved the works. That's how they came down to us. Because the Dark Ages were horrible, especially in the western part of Europe. I mean, just horrendous. After the Black Plague of 524, it devastated Constantinople, but it went into the Western Europe, and it basically became a ghost town. Everywhere was ghosts. I mean, it's just no one was around. Very few people around. Terrible time to be alive. Okay. And just a quick couple more here. This guy, Pacioli, double entry accounting. He's the one that came up with it. Berlioz not here, okay? But he also, you can see the influence of the Greek works. I mean, the rhombo, cubo, octahedron, and geometric tools. See again, the slate, the straight edge. Okay, a little dodecahedron here. Franciscan friar. See again, religion. What did I say? Religion played a huge role. It saved a lot of the Greek works. And then finally, you know, Johannes Kepler. You can see he was influenced directly before he came up with his planetary motion that said that all planets moved in elliptical orbits. Okay? That you can see, if you remember, these are platonic solids. He thought he could nest platonic solids to make meaning. He thought this is how the universe was constructed. He didn't know, right? But this is influence from the Greeks. Of course, he changed it. But how did he get the ideas of ellipses? Got it from Apollonius. So, very interesting. I mean, I think it's fascinating. These pictures. It's not the only one that drew those kind of pictures. So, we're going to finish up the Parthenon. I mean, to build something like that, it takes a tremendous amount of engineering, which requires a lot of mathematics, science, and so on. The problem is with today, most people don't realize what it takes to build something. What it takes to create something. Because we just go to the store and buy it. Can you guys build a car? Can you sew your own clothes? I mean, we don't know what it takes to do something, to have something. So what happens is when people look at these things, get a bunch of guys together, they can build it. Like the Great Wall, just a bunch of guys building rocks on a hillside. No, there's a lot of engineering. It requires a tremendous amount of knowledge of science, which, as math is the queen of sciences. And it influences us to this today. And this is in Tennessee. I'd like to go see it. So it influences even of our time, modern time. This is original. This is one built in Tennessee. Yeah, pretty cool. So it influences us today. Even a lot of the columns, you know, of banks and things like that, they're all, I mean, architecture still influences us. Philosophy influences us. The idea of, you know, logic, you know, axioms. I mean, these are things that these people came up with that we know of. I mean, it could be other folks as well, but our society would not even be remotely the same if we didn't have the works from the Greeks, for sure. All right. Was there any questions? I think Kirk had a question.
Yes, there.
How do you think correct nowadays mathematics is? Because just like you said, it got corrected over the years, over like thousands of times and stuff, and people actually like learn the incorrect things for ages. And do you think it's on this credibility phase right now, or what do you think?
You mean like how has math changed since which originally in Greece, or when they copied it, did it change?
I mean, do you think we can learn something incorrect nowadays that will be like totally nonsense for the past?
I mean, well, I mean, like for example, like some scientific theories, you know,
Yeah.
that happens. Scientific theories, like I said before, they get knocked down. Every generation they change. The idea, for example, what was a good one? People used to use mercury. They thought that mercury would, you know, heal wounds. Well, of course, mercury's toxic. It was actually a science. People thought, well, you know, this is good. This is actually will, you know, save you from whatever. That's just an example. But yes, I think the whole idea is you want to learn. What they're saying is, yes, you cannot know everything for sure. Everything is relative. The whole point is, can you use to have the right processes in place to make arguments, to make those arguments. So yes, even though you may learn something incorrectly, can you go back and question it again and try to come up with a new theory? So the whole idea with the Greeks, they would say, I would think, that is, learn the proper way to reason, and then, you know, the truth as much as possible will come out. So I don't know if you're asking. Yeah, go ahead, Darren. Yeah.
Any other questions?
Hi, Mike. Thanks very kindly for your paper. You have dredged up some repressed high school memories of my poor mathematics performance. Question is, I noticed when you were talking about the inductive, deductive reasoning and your examples, I was struck by the difference between some of your examples was language. The language that was used. The language would shape the determination or the confidence in, I guess, maybe the reasoning or the proof. Is that a modern thing? Have we imposed that language subsequent to the Greeks, or would they also have been relying on language to help them understand their reasoning and the induction, the deduction, and whatnot?
Wow. I don't know all that. That probably will become from an English person like yourself. But I would think, yeah, the whole point, I guess of what I'm thinking you're saying is you're looking at the premises. Are the premises right or wrong? Yes, and it would take time. They would have to take the premises and just kind of beat it to death. Can we get to the heart of it? Can we get to something so basic that we can say for sure that everyone can agree it's yes or no? And so like numbers, like 1 is a number. We can say, yes, 1's a number. It's done. But if you get something more complex, some people may agree, some people may not, right? So the whole point to get rid of bias, they think, is can we get a premise that's so basic that everyone knows, and then take those basic premises, use logical deductions, and create something bigger. So yeah, language, I would think, yeah, it's full of biases and full of meanings that trend. I mean, many words have changed meaning even in the last few years, as you know. Yeah. So I don't know what the Greeks thought about language. That's interesting. But I would think that that's what they're trying to do. Even with mathematics, you want to get as basic a premise as possible that everyone can say, yes, this is true. This is agreed upon. Yeah, so, okay.
How much in conversation were these people with one another? So for instance, you covered about 600 years worth of history, and you touched on some of the most seminal people. Were they aware of the people before them by name? Or, because so much of what they did is based on the previous things that they've learned, since that is what math really is.
Right.
Would they have known the name Pythagoras, even though we don't really know, Pythagoras never really wrote anything down. We only know because of his students who he is. So would they have known Pythagoras? Would they have known these people that came before them by name?
Yes, I understand that's true. Like I believe Socrates never wrote anything down, right?
Right.
Yeah. So Aristotle was a student of Socrates. But yes, am I correct, or Plato? Socrates, yeah. Plato was a student of Socrates, right?
Yes.
Yeah, okay, I get this all mixed up. I forget. Anyway, but yes, they did know. For example, Aristotle made critiques of Zeno. Yeah, because he was looking at Zeno's paradoxes. Well, I don't think you really got the idea, kind of thing, essentially. But yes, people definitely were aware of each other. And you're right, Pythagoras is an interesting character. No one really can tell or knows if Pythagoras actually came up with this theorem or not. Remember, it was a group. Pythagoreans were a group. Maybe it's some guy or some woman in the group that came up with it. Or maybe they came up with it together, or maybe they found it from somewhere else. No one really knows. So Pythagoras is a weird character. He's a cult leader. That's what he was. He's a cult leader. Yeah.
Anyone else? All right, I'd like to thank Mike for your time, and thank you for your lecture.
Thank you.